Section 13.4, histograms. Alright, so previously we were looking at ways of grouping and graphing categorical data. Now we're going to move to quantitative data. And a histogram is the name given to a bar graph that is for quantitative or numerical data. So we call it a bar graph when it's categorical, but we call it a histogram when it's numerical. And the vertical scale on a histogram could be frequency, relative frequency, or density, and we'll look at examples of all those types. And one of the advantages of working with numerical data is there's a fixed order that the bars would go in. When it's categories, you could rearrange it really in any order you want, alphabetical, from highest bar to lowest, lowest bar to highest, and all kinds of different things. But when it's numerical data, you would always order the bars based on the numbers that the bars represented, so they'll always be in a set order. And that allows us to start talking about shape. So with quantitative data, we are often interested in determining the shape of the distribution of the data, and the graphs below show a few common distribution shapes. We have bell-shaped, bimodal, where we have two peaks, left skewed or right skewed. There's other shapes as well, but those are the four that we're going to talk about the most in this text. And with left skewed and right skewed, what you want to be able to think about is the order of things. So when there's only a single peak to a data set, we call that the mode. And if your data set is left skewed, then the median will always be to the left of that peak. And the median is that halfway point through a data set. And the mean, or the average, will be pulled even to the left of that. So when you have outliers or low values over here on the left that are far from the peak, those pull the mean or skew the mean to the left of the median and to the left of the peak. For right skewed, it's the opposite. Your outliers are on the high side, and that pulls the mean or the average to the right of the peak and also to the right of the median. And when we say it pulls the mean to the right, you could also say it skews it to the right, and that's where that language comes from. If your data is symmetric and only has a single peak, then the mode and the mean and the median will all be the same. And we'll talk more about mean and median in later sections, but the median is halfway through the data set, 50th percentile is another way of saying it. And the mode is the peak and the most commonly repeated value. The mean is what you're used to as the average. So let's look at a few important facts about these distribution types. An outlier is an extreme value that is far away from most of the other data values and also far away from the peak typically. In a unimodal distribution, that's one that has only one peak. If there are two peaks, then we would refer to this as a bimodal distribution. And bimodal distributions often represent two distinct populations mixed together. So just a quick example to talk about some of these shapes and how bimodal fits into that. It's usually the case that if you look at a population of men, that you get a bell-shaped distribution for their heights. Same thing goes for women, but if you throw men and women together and you just look at the distribution for the heights of people, then you might get a bimodal distribution where you have the peak for the average height of women and another peak for the average height of men. That will not always be symmetrical like this because there might be more men or more women in your population, and that could affect which of the bars is taller, but this is what it would look like perhaps if they had the same amount of men and women. So a lot of times when you have two peaks, you think there's probably two populations blended into one, like men and women blended together for the category of people. All right, let's look at some more of these bullets down here. A unimodal distribution is also often referred to as, let's see, that's going to be either left or right skewed if the tail on the right side is substantially longer than the tail on the left. So the tail on the right side, this is the tail, is substantially longer than the tail on the left. So that would be a right skewed distribution. So I would think this other one must be left skewed, but let's check to make sure. A unimodal distribution is referred to as left skewed if the tail on the left is the longer tail, substantially longer than the tail on the right. Okay? And then finally, if the two sides of the distribution are mirror images of one another, then we say that we have a symmetric distribution. And typically we think of symmetric and skewed to kind of be opposites of one another. So a data can't be both skewed and symmetric. So we're usually trying to classify a data set as one or the other. So here we have left skewed and here we have right skewed. This is a symmetric distribution and so is that one. All right, let's look at an example that starts talking about histograms, also starts talking about the shapes of distributions, and then I referred to things like the median, 50th percentile, and we haven't covered those yet, but those will come up in this example as well. So the relative frequency histogram shown below represents the ages of a sample of 1,089 people that were stopped by the police in New York City on December 1st, 2012. Some of the people were younger than 10 or older than 65, but there were too few to create a visible histogram bar. All right, so describe the shape of the distribution and what does it mean in this situation. So if you look at this picture and you compare it to the shapes we just saw, we have a long tail on the right and a very short tail on the left. So that matches best with this right skewed shape right here. So that's the first thing I'm going to say, because that longer tail on the right, this is a right skewed distribution. And then what does that mean in this situation? So it means that because these are lower relative frequencies, that it was less common for the people who were stopped to be older. Over here we have our tallest bars in the 15 to 25 range, so younger people were much more likely to be stopped by the police. So most of those stopped were younger. And very few of those stopped were older. So that's definitely something we want to be able to think about when somebody says that our distribution is right skewed. We want to think, what does that mean? It means the peak is on the left side. Where the peak is, those are the things that happen more often. So it's more common for those being stopped by the police to be younger folks. Not so much in the 10 to 15 range, but like in the 15 to 25, maybe even 15 to 30. Those were our tallest bars. And so then not only were the percentages lower for those that were older, but for those that were very older, like in the 60 to 65 range, those people were very far from where the peak were. So those are our outliers, the ones that are far away from the peak, and we had much bigger outliers on the right than on the left, which is why we would say this is a right skewed shape. All right, let's look at the next question. Estimate the proportion of people stopped by the police who were at most 19 years old. So at most translates to less than or equal to. So we want to know what percentage of those stopped were less than or equal to 19 years old. So this line right here separates those that are 20 and above from those that were 19 or younger. So it looks like we have two bars falling into that category, the 10 to 15 and the 15 to 20, but really the 20 is in the next class. When these histograms are drawn, whatever number's on the border, that's the beginning of this class, and the previous class goes up to everything below that number of 25, or in this case below 20. So we have our 10 through 14-year-olds here, and then we have our 15 through 19-year-olds here, and we want to add every one of them that meets this description of at most 19 or less than or equal to 19. So the total there, I guess I'll stick with the color matching, would be the 0.02 plus the 0.29, so that would be 0.31. And they just said proportion, so we can leave that as a decimal. We can think of that as 31%, but they said proportion, so I'll just leave it in a decimal form. All right, and then identify which class contains the 50th percentile, and are the observations in this class typical? So let's go ahead and first define the percentage and then think about what they mean by a typical value, and then we'll go back and answer that question that involves those terms. So percentiles, the 50th percentile of a data set is the value that separates the lower 50% of the data set from the upper 50% of the data set. If they gave different percentiles, like the 30th percentile, that would separate the lower 30% from the upper, and then we'd think about what's left over. If there's 30% below, then there would be 70% above, so that upper 70% would be the other part. So the number on the percentile is always the percent that's lower. So you can't tell with 50th because it's 50 on both sides, but the 30th percentile, the 30% was the lower part. And that's always the case, that the lower percentage will match the number on the percentile. And then they ask, so let's go ahead and do that part real quick. Actually, identify the class that contains the 50th percentile. So what I want to do is go to this chart, and I want to kind of keep a running total of what the percentages are. By the time we get to the 15-year-olds, we only have 0.02 or 2%. If we add on up to the 19-year-olds, now we're at 31%. If we add the next group, which goes up to 25, that's another 27%, bringing our total to 58. So when we were right here, just finishing off the first two bars, we had 31%. By the time we ended the third bar, we had 58%. So somewhere in this bar right here, we went from 31% to 58. We must have crossed through 50%. So the 50th percentile must land somewhere in this bar. We do that with a capital P. So P50 is somewhere around there. So which class contains the 50th percentile? I would say that's in the class 20 through 24. So somewhere in that age 20 through 24 is an age that cuts the percentage of people that were stopped by the police in half, a lower half and an upper half. Now they want to know, are these observations typical? So let's go ahead and look at that definition real quick, and then we will answer their question. A data value is considered to be a typical value if the relative frequency for this class, for the class the data value is in, is greater than a majority of the other classes. That is, it lies in one of the taller bars on the histogram. So then they just want to know, is that class where we found our 50th percentile typical? So we just want to know, is that one of the taller bars? And when we go look at that, it wasn't the tallest bar, but it was the second tallest bar out of a whole bunch. So I would say that yes, it is typical. And that would be because it is one of the taller bars. So we think of the height of a bar as representing how common it is for that to happen. So the taller the bar, the more common it is. The shorter the bar, the more rare it is. And that was our second tallest bar, so it's definitely one of the more common ones. And according to this definition, that would also make it a typical bar. All right, we have one final example here, and this one involves a density histogram. So let's go ahead and define that. A density histogram is one where the area of each bar is the same as the relative frequency of the class. So remember that the area of a bar is its length times its width. So they're saying that if you took the width of this, which is 5, and then let's say height of the bar, so do like base times height for the area. The base is 5, and the height is like 0.02 something. If we multiply those together, they're saying it's 0.112, and they'll have us work on that a little bit down below. All right, so let's go ahead and have a look at that. Let's see, so what are we talking about here? The 2011-2012 tuitions in thousands of dollars of a four-year private universities and colleges are described by the density histogram shown below. Show the work that explains why the area of the tallest bar is 0.18. All right, so the area is 0.18, and that's equal to the base times the height for that bar. And the base of that bar is going from 20 to 25, so that's 5. So 0.18 is equal to 5 times something. So 5 times what? So if I were just to estimate the height of that bar, it looks like it's kind of right in the middle between 0.03 and 0.04, maybe a tiny bit higher. So maybe that's like 0.36, just a little bit more than halfway between the, sorry, not 0.36, but 0.036, right? It was 0.3 and 0.4, so it would have to be 0.3 something. So it looks a little more than halfway, so I'm going to say 0.36, and let's see if that works. So if I bring in the calculator on that, and I do 5 times 0.036, I get 0.18, which is a check. So that does seem to work. All right, so that's how what these densities represent is the base times the height or relative frequency, or sorry, the density of that bar, and that would be the relative frequency. All right, so this didn't print super well, but that says density right there. So the density is the result of taking the width of the bar times this number gives you the relative frequency. So it's kind of a strange way to do it, maybe, but if they number with this density, then this ends up being relative frequency, and what's nice about that is the total area will be the same as the total of relative frequency, which is 1. And it turns out in stat we use that idea a lot, where the total area is 1 of a graph, and that 1 represents relative frequency. So we want to get in the habit of thinking of area of a bar as representing the relative frequency, but that only works if it's a density histogram. All right, so let's look at some more questions about this. Identify the class that contains the 50th percentile, and our observations in this class typical, so it's a lot like our last one. So we're going to think about coming up with a total and seeing when that total crosses 50%. So we just have to remember that the relative frequencies on a density histogram are not these numbers, but these areas. So we have 0.03 plus 0.12 plus 0.13 plus 0.12. Let's see where we are if we do the first 4. 0.4, which is 40%. So at this point, we're not to the 50th percentile yet. If we add the next one, though, 0.18, then we're at 58%. So right here we were at 40, and right here we were at 58. So the 50th percentile is somewhere in that group. All right, so identify the class that contains that. So how do we want to describe that? That was in thousands of dollars. So the class that went from $20,000, I'll just put 20K, through 25K. Somewhere in there is the 50th percentile. So what that means is that half of the, let's see, 4-year private not-for-profit universities and colleges, about half of them have a tuition that's somewhere below, let's say, $23,000, and the other half above $23,000. I don't know the exact number, but it's somewhere in that class. Would separate the cheaper 50% from the most expensive 50% of these types of universities. And then our observations in that class typical, for sure, because that's the tallest bar that we have. So are they typical? Yes. And why? Because that was the tallest bar. And if it's the tallest bar, then for sure it's taller than a majority of the bars. It's taller than all the other bars. All right, let's see what other questions they have for us. What proportion of the institutions had tuitions less than $30,000? So there's a couple ways of going at that. one of them would be to just draw that line at 30,000, and they said less than, so we would just add up all of the decimals that were below that. So 0.03, 12, 13, another 12, another 18, and then also the 17. Alright, so we actually almost had that done already. It was the 0.58 if we added up to here. If we just add in that 0.17, that would be those four plus this one plus that one. Those are the 6 we have listed. So that's 0.75. And did they ask for proportion or percent? They said proportion, so that would be the answer. And we'd probably interpret that as a percent, so you could also say 75% of these types of institutions had tuitions less than $30,000. All right, I'll show you that another way in just a moment, but first let's look at Part D. What proportion of the institutions had tuitions of at least $35,000? So to do that, at least 35,000 is 35,000 or more, so we'd want to add these two together. We want to go this way, but the problem is we don't know what those two are. So here's the trick. We know that because these are relative frequencies, these numbers, we know they have to add up to 1. So I can bring in the calculator and I can add all of them up. So 0.03 plus 0.12 and so on. And I kind of do this in my head too. I know that when we went up to this line we got 0.75. Adding another 0.12 should be 0.87. So there it is. If you take that and you subtract it from 1, it means that these two bars right here must make up the remaining 13%. And you could then, because these happen to be just as tall as each other, you could even divide that by 2 and say each one of those must be 0.065. And again, we're doing that because we know that all of these have to add up to 1. And when we added up all the ones that were given, they added up to 0.87. Subtract that from the total we know we're supposed to get. It says how much is left over. Cut that in half, and that would be for each bar. Again, the cut in half I can only do because the bars are the same height. Alright, so what proportion of them had tuitions of at least 35,000? Well, we can see that it's the 0.65 plus the other 0.65 now that I've got it labeled. Sorry, that would be a plus sign, which is 0.13 or 13%. They said proportion, so that should be my answer. But what I really did to get that is I did 1 minus the 0.03, the 0.12, the 0.13, the 0.12, the 0.18, the 0.17, and the 0.12. When I subtracted all those from 1, I got the 0.13. So speaking of that idea that we can use subtraction to get an answer, let's go back to Part C for a minute and say what proportion of the institutions were less than 30,000, right? So that was all the ones, if we took this line right here, that was all of these. But what we could do, that would be faster, instead of adding up 1, 2, 3, 4, 5, 6 bars, I could also have done 1 minus these 3 bars, and that would have worked too. I couldn't do it at the time because I didn't have all the bars labeled. But so I'm going to subtract from 1 these 3 bars, so 1 minus 0.12 and minus the 0.065 and the other 0.065, and that should give us the same 75%. So taking advantage of the fact that we know the total is 1. So let's just check that. 1 minus 0.12 minus 0.065 minus 0.065. Same answer as before. So it's important to remember that the total of these bars equals the total relative frequency of 1. That can do 2 things. It can help you figure out missing bars by knowing what the total is, and it can also make things go a little shorter. If somebody asks you to add 6 out of 9 bars, maybe just subtract the 3 you don't want from 1 as another option. Alright, let's go ahead and look at the final question. What shape best describes the distribution of the tuitions, and explain? So let's see, our peak we have two bars that are about the same. So here's our peak, is in this zone. And then we have 4 bars to the left and 3 bars to the right. If you said this is my tallest bar, that's the peak, you have 4 bars to the left and 1, 2, 3, 4 bars to the right. So we might say that this is a roughly symmetric shape, maybe even kind of a bell shape. Not a smooth bell shape for sure, but we've got the tallest bar in the middle and 4 bars on each side. The symmetry is not perfect. But there's not really like a long tail on one side and the side more so than the other. If this is our peak, we have 4 on each side, so I would say it's roughly symmetric and maybe even roughly bell-shaped. Okay, that wraps up section 13.4.